Hey guys, this is Miss Wiesner, and I'm going to go back over the constant rate of change in the lesson that we were going to do today on proportional relationships, because I think I need to backtrack and talk more about what these things are and how they relate to math and in the real world. So my apologies. I think I went too fast, assuming too much, and I really am sorry if I cause a lot of you any stress, because I don't want you to feel that. You know, I'm going to do whatever I can to make you successful. So let's just talk about the basic. So this is a linear relationship is what we're talking about right now. There's different types of relationships, and when I say relationship, I'm talking about relationships between data. So if I wanted to look at, data's taken everywhere, but we're only looking at two pieces of data, and it's different depending on which situation you're in. So if I am a store owner and I want to count how many customers come in my store every hour, then I'm going to be comparing the time, each hour, and then I'm going to count the number of new customers. So then I can take that data, put it in a table or some other form, and I can analyze it. And I can tell, okay, well, there's a steady string of customers that come in, as the time that my store is open goes up by the hour, the number of customers new customers that come in rises as well. So it might appear to be a straight line, or it might appear to be a little jumpy, like maybe the customers drop off a little bit around lunchtime, or maybe they increase around lunchtime, depending. So that may or may not be a linear relationship. A linear relationship, when you take the data that you're looking at and you graph it on a line using your data, it's going to make a straight line. No ifs, ands, or buts about it. It's going to be a straight line. Not one single point is going to be out of place. It's going to be completely straight. That shows that it's constant, that the change that's going on is a constant change, that as the time increases, so does the number of customers I have, and it never deviates from that. Okay? Now, that's just one example. Another example would be the corona or the COVID-19 virus. If you want to look at the number of new cases that we get every day, so you might be comparing the days with the number of new cases. So as each day increases, you are looking to see how many new cases are reported. Now, I can tell you right now that's not going to be a straight line, because that would be more of an exponential growth, like maybe something's doubling every day, which I don't know that that's what the COVID virus is doing, but the COVID-19, but that's an example of what I'm talking about. So if something is doubling or doing something like that, it cannot be a linear relationship. That's a different type of relationship. It can be a line, yes. It can be on a graph, yes. It can be in a table, yes. We can try to see if it has a constant rate of change. It will not, but it'll be important for that particular graph that we know what we're looking at. Basketball that bounces. If I wanted to look at the number of bounces, the height of the basketball as it hits the ground. So the first bounce, it fell from this height, and by the second bounce, it fell this far. Third bounce, that's not going to be linear. It doesn't bounce the same amount every single time because of gravity and all that science junk. Okay, so I just want to give you a little background. Sorry if I bored you, but I think it's real important that you understand that we're only looking at one type. Okay, and when we're looking at our data, we're going to be looking at data in tables. The data is going to be maybe in a graph, a coordinate plane, which primarily would be the first quadrant. So remember, you go over X and up Y. Ordered pairs, these are the coordinates that you use to plot graphs. and then equations, and then a few other things. But these are primarily, right now, these first three are primarily what we're looking at. And then we'll get into the equation part after we get through these first couple of lessons. Okay, and for this slide, I just wanted to show you just some examples of relationships that may not be linear. This would be, and I tried to get it to copy and paste, but maybe I'll just give you the link. This is a very general description of what the graph looks like for the COVID virus 19 outside of China. So it's not just in the U.S. So you see it starts off kind of slow, and then all of a sudden it starts increasing, and because as more people get infected, then the more it doubles, and then so on, and then they infect two people, and then they infect two people or three people, whatever it is. That's why this graph is going up like this. This here is a table. It's very nasty looking, I'm sorry, but if you see the Y's and X, I put them backwards because we always deal with Y over X, which is really weird because X comes first in the ordered pair. But you see your Y's are doubling each time as your X's are going up by 1. So this would not be a linear relationship because you can't, that's not a constant rate of change. You can say, well, it's constant because it's going up, it's times in by 2 each time, but that you said it, the fact that it's multiplied by itself twice, by itself each time it goes up, that does not make it linear. Now this is my rough drawing. I love to watch, and give a shout out to Air Disasters, and y'all think I'm funny, but go ahead, Nabil, tell us about it. If an airplane, I'm just kidding, if an airplane is coming through, I can't believe I believed y'all. Y'all are so mean. Poor Nabil. If an airplane is coming through, when I'm looking at, they're looking at the people who try to investigate airplane crashes, they're looking at data. A lot of it I don't get. It's like way over my head. But what they're doing is they're looking at the approach that the airplane makes when it comes into land. So they usually do what's a leveling off approach. So they'll be going like this, and they go, okay, I'm getting ready to land. So they'll go down a little bit, and then they'll level off again. They'll go down a little bit and level off again, and they go down a little bit, and then they land. So that would be a straight line right here. But in one crash, some people were looking at what pilots were doing was what's called the slam dunk approach, and you can look it up on the internet if you don't believe me. A slam dunk approach means that they're flying up here at a high altitude, and then all of a sudden they wait to the very last second. They don't stagger it out like they do here. They wait, and then all of a sudden they decrease rapidly and then land. And they're doing that for several reasons. Maybe to avoid mountains, maybe to avoid a spot up here where there's freezing temperatures and they don't want to be up here very long, so they'll just slam dunk through it. Okay, so that would be a linear relationship. Even though it curves at the end, if I'm looking at the landing part of it, that's linear. Okay, the first example that we did, now I know I'm doing all these again, these are still, you can still access this in your slideshow if you want to, or Google Slides, but I just feel like I needed to explain it a little bit better. This is a table of data, okay? It is some guy who downloads music from the internet, and you should always say what your data is. So this is number of songs downloaded, and he wants to know how many he can per minute, or if that's going to be a does it vary, does it change depending on the song, or is it going to be a constant change? So there's two ways you can look at this graph. One way was to see if it's linear. Another way to look at it is to see if it's proportional. We haven't done proportional yet, but when I saw some of your work, well, only 2 of you turned it in, but some have questions. But when I saw one person turn it in, I realized, man, she's right on the money. but I was afraid she was confusing the two relationships since I didn't go over proportions yet. So I want you to pay attention to this. You can look at this. I can look at how this 0 relates to this 0, this 1 relates to this 2 to 4, 3 to 6, 4 to 2. That's great. Sometimes if I look at it this way, it's going to give me the information I need, okay, depending on what the data is. But this guy, when he didn't download any minutes, he didn't, yeah, at minute 0, he hadn't downloaded any songs, okay, because he hadn't even started yet. So my first point was 0, 0. Then after 1 minute, he downloaded 2. When he was on minute 2, he had downloaded 4. Minute 3, he had downloaded 6. And minute 4, he had downloaded 8. Okay, it's important, yes, at some points you want to look at how the graph is changing vertically or within the numbers. But for a constant rate of change, or to see if it's linear, this is very important. First, you got to see if it's linear. We're looking at change in Y over the change in X. Now, not to scare you with this, it's not hard. It's just I want you to get used to this. So what you're going to do is look at, and I don't care which way, time is always going to be X. We'll talk about that later. But so let's see how the number of songs increases. So look at it. I'm not going up and down, right? I'm looking at how this is increasing or decreasing. Okay, so the change in Y is that it's going up, and it's going up 2, 2, 2, and 2. So my top number is going to be 2. That's perfect. My bottom number is going up by 1 each time, correct? So I would have 2 over 1, 2 over 1, 0 over 0, and 2 over 1. Okay, so since all those are the same, this is the constant rate of change. And that shows that it is linear. It's going to make a straight line when we graph it. Now, I think we just graphed it I wanted to graph it just to prove to you that it does make a straight line, and it's very hard when you're trying to use Google Slides or PowerPoint or whatever. But the ordered pairs, if you wanted to graph this to see if it was a linear relationship, you know that X goes first. So we have 0, 0, and then the second one was 1, 2, and then my third order pair was 2, 4, and then I can go over to here 3 to 6, and then 4 to 8. So this, when I plot all these, you can see that this would indeed make a straight line if my dots were straight, but cut me some slack here. So if I would chop off the 0, 0 if I'm trying to look at whether or not this was a linear relationship. And so let's suppose you're given this and you had to find out if it was a linear relationship and not the graph. You're just looking at the ordered pairs. You could still see how the Y's are increasing and how the X's are increasing. And take that and make your decision. Okay, on this one, you just need to find out if it's linear. And if it is linear, what's the constant rate of change? And if it's not linear, why not? Okay, I'm not going to pay attention to this, okay? I don't care about the relationship between 3 and 170, 6 and 140. That's not a big deal to me. So I don't even care about that right now. What I care about is how is the, and I'm assuming that this is Y and this is X. So how are the Y's changing and how are the X's changing? Okay, now this is on your slide. I'm just doing it again to try to explain a different way. So what's it doing from 170 to 140? Well, it's going down by 3. And this is 140 from 110, it's going down by 3. 110 to 180, it's going down by 3. Okay, from 3 to 6, it's going up. Wait. 7. I'm sorry, not 3, it's 30. Duh. Thought that was weird. It's going up by 3, and 6 to 9, up by 3. 9 to 12, up by 3. Okay? Now, this doesn't look like the song one did at all. Because if I take these and I write them down, I have negative 30 over 3. That takes care of this one. I have negative 30 over 3. That takes care of this one. And then negative 30 over 3. It takes care of this one. This is important because you're not always going to have every single piece of data in the middle. Maybe it'll skip. Maybe it'll skip from 3 transactions to 12 transactions, and you're missing these 2 pieces of data. If you do it this way to find out if it's linear, it's not going to matter. So what is this reduced? Negative 3 over 30 is negative 10. Negative 30 over 3. Negative 30 over 3 is negative 10. Negative 30 over 3 is negative 10. So the constant rate of change is negative $10. So what this means is, as the number of transactions increase, the amount or the balance in your account decreases $10. Okay, on this one, we want to see if it's linear, just like with the others. All right, I don't care about this. Don't care. So time is X, temperature is Y. So from 95 to 90, it goes down 5. From 90 to 86, it goes down 4. From 86 to 82, it goes down 4. I'm not going to worry about this because, yes, that 5 is different, but maybe it's still going to work out. You don't know until you know. So from 5 to 10, it goes up 5. From 10 to 15, it goes up 5. From 15 to 20, it goes up 5. So when I look at Y over X, it's negative 5 over 5, and then negative 4 over 5, and then negative 4 over 5. So this is negative 1. That's not the same as those two. So because one of them is different, this is not linear. If I had time, I would show you on a graph. Okay, this is an ordered pair. So they're wanting you to take ordered pair. This is a graph. They're wanting you to take this graph to see if it is a linear relationship. Well, duh, it looks linear, okay, but we don't know that for sure. So where do you get the numbers from to compare? And there's this neat graphing program that I want to show you. You can put in ordered pairs, and then it'll create a table for you. But you first got to know how to put in ordered pairs. So my first dot is over 8 up 80. So it's 8 and 80. My second dot is over 16 to 60. And then my next dot is 24 to 40. Okay, so those are my ordered pairs. Now, you could put them in a table if you wanted to, but I know that my first numbers represent X and my right-hand numbers represent Y. Why does he have to bother me while I'm doing this? Oh, going to the dentist. Social distancing. Dentist. My husband has an immune deficiency. He's had a stroke. He can't be going to the dentist. What's his problem? Well, that's his life. 80 to 60 it goes down 20, right? And then from 60 to 40, it goes down 20. And you'll be able to tell after a few lessons that that's going down. And then, well, you can see that. 8 to 16 goes up 8. 16 to 24 goes up 8. I'm not caring about these relationships between these numbers. I don't care. All I care about is how Y is changing and how X is changing. Well, if I wrote it down as Y, change in Y over change in X, then this is the same. So I know it's linear, but I need to find the constant rate of change, and it needs to be in reduced form. So that would be negative 5/4. Constant rate of change is negative 5/4. So that means that, see, and they put time up here on the y-axis, and I don't know why, because it always goes this way. But anyway, they're just saying that as the number of volunteers, it doesn't make any sense. Anyway, I can't. Okay, here's another one for you to see if it's linear or not. And remember, you can always fast forward if you're starting to understand this. And this is just exactly the same as what's on your PowerPoint. So I'm going to look at the change in Y. So it goes from 6 to 12, that's 6. From 12 to 18, that's 6. And then how do the X's go up? Well, the X's go from 5 to 10, which is 5. 10 to 15, which is 5. So is it linear? Absolutely it is. All right, what's the constant rate of change? Well, it's 6 over 5 and 6 over 5. That equals, and they're reduced, so it's 6/5. All right, this one's hard to see. I used that, well, the numbers were very large. And so I used the Desmos calculator, which is what I'm going to show y'all later. So that's a 1, and so this is 1, that's 2, that's 3, 4, 5, and 6. And then when I copied this, it took off the altitude. This is an airplane. Okay, so let's look at your ordered pairs. Okay, starting off at 3,500. So that's at 0. So my X is 0, my Y is 3,500. That is the altitude of the airplane. So then that was at minute 0. So at minute 1, we don't know. Minute 2, we know that he was at 3,000 feet. So we don't know minute 3, we don't know minute 4 or 5. We know minute 6, he was at 2,000 feet. Okay, he's not doing a slam dunk. He's not at that point yet, I don't think. But anyway, yes, these kind of skipped around. We were missing some data in between the points. Doesn't matter because we're looking for how Y changes and how X changes. So that goes down 500. That goes down 500. And then as the time goes up this goes up by 2. I know you can't see it that easy. And then 2 to 6 goes up by what? By 4. Okay, so I'm so stupid. That's going down 1,000. Okay, so oh my God. I hate that he interrupts me. Oh, I just want to leave me alone. I'm sorry, I love them. Okay, stop. All right, so the change in Y, first it goes down 500 at minute 2. And then at minute 6, or the next change would be 4. And then that change was from 3,000 to 2,000, which is a drop of 1,000. So he dropped 500 feet in 2 minutes, and then by 4, as the time changed by 2 minutes, he had dropped 500 feet. When it changed by 4 minutes, he was down 1,000. That doesn't matter. What matters is what it reduces to. Because right now you might not think that it's a linear relationship, even though that you see that it is. Oh, don't tell me this has been out this whole time. Oh my God, I don't care. Okay. Negative 250 over 1, and then 4 we're going to 1,000, negative 250 over 1. So yes, it's linear. And it has a constant rate of change of negative 250 feet. They just want to see, the air traffic controllers just want to see that it's going in at a constant rate. Okay, it goes actually 36. Now, this still doesn't look linear to me, so I'm going to take my data. I'm going to look down here at the bottom. It's easier to see, so I'm going to go y over x. 9 over 3. I'm going to say 12 over 4. And then 36 over 12. Okay, what do all of these, do these reduce down to the same number? If they do, then I'm in business, because then it would be a constant rate of change. So 9 divided by 3 is 3. 12 divided by 4 is 3. 36 divided by 12 is 3. So my constant rate of change is 3. So the change in y and the change in time is 3. So as the time increases, the cost increases by $3. So as the hour goes up, the cost goes up 3 to run your computer. That's assuming you don't do anything else to it. Right. Okay, so 0, 0, I'm not going to worry about this yet. So I'm going to look at the retail price and the sale price. We'll say this is X and this is Y. I don't know if it is or not. We're just going to make it that way. So that goes up by 5. This goes up by 5. This goes up by 5. And so does this. 10 to 20, that's 10, 10, 10, and 10. Well, I don't have to write all these down because I know they're all the same. I just need to write down 1, the change in y is 5, and the change of x is 10. So that reduces down to 1/2. So the constant rate of change is 1/2. All right, now for the third one, so it means as the retail price increases, the sale price is cut in half. Okay? It increases by half. So time goes up 1, 1, 1. Total help, that's 12. That's 12. And then, oh my God, 24. Why would that be? Okay, so let's look. You've got 12 over 1, 12 over 1, and then 24 over 1. So this is not a linear relationship. So this one would have been yes. This one would have been yes. But this one doesn't have a constant rate of change. It changes by 12, and then all of a sudden 24. So it is not linear. Okay, looking at your graphs, can you tell this is linear? Oh, by looking at it, absolutely. Write down your ordered pairs, and for the sake of room, I'm just going to write them down. I got 0, 0. I have 1, 2. They're given to you right there. And I've got 3, 6. Now your first number is X and your second number is Y. So my change in my X goes up 1. Change in Y, that goes up 2. And then that goes, well, I'm sorry, 1 to 3 goes up 2. Sorry. And then 2 to 6, that goes up 4. So what you can do is make fractions out of these. 2 over 1 and then 4 over 2. And as long as they reduce to the same thing, then it's a constant rate of change. 4 divided by 2 is 2. So yes, and the constant rate of change is 2. So this one would be 0, 0. That's that first dot. The second one is 2, 10. And then the third one would be, it'd be 4, 20. They're leaving out some points for you, and they do that a lot. So just be careful of it. From 0 to 2, it goes 2. From 2 to 4, it goes 2. From 0 to 10, it goes 10. From 10 to 20, it goes 10. So it looks like it's linear, obviously. So what's the constant rate of change? It's 10 over 2, which is 5. So yes, it's linear. The constant rate of change is 5. Okay, and my little Allie Wiesner says, stay tuned for proportional relationships linear. That'll be coming up in a little bit.